So let's talk about local extrema and quadratic surfaces. It turns out that discriminant thing that we learned with local extrema has something to do with quadratic surfaces. But before that, let's talk about Taylor polynomials of a function, basically, of approximation of a function. So let f of x and y have a critical point A and B. That actually is not to do with the Taylor polynomial, but I just need that for a specific thing. And let f have a convergent Taylor series. Second degree Taylor polynomial approximation of f about A and B looks like this. Now I tell you why I wanted the A and B to be critical point, because I want this term and this term to be 0. So looking in this, I can see there's a constant and there is a multiple of x minus a to power 2, multiple of x minus a times y minus b, and a multiple of y minus b to power 2. If you translate the graph of a function f, so the critical point a, b, and f of a, b moves to 0 and 0, 0, then the Taylor polynomial looks like something like this. It's z equal to a x squared plus b xy plus c y squared. And so that is the preferable shape for me, because at least I can tell this is a quadratic surface quickly. I mean, the other one I could tell, but I don't have to worry about the translation that is happening. So all this busy surrounding goes away, and it's down to x squared, xy, and y squared. Now, again, when I'm doing when I'm trying to recognize the quadratic surfaces, I like the power 2s and everything, but I don't like the b times xy, right? So how do I get rid of that to have this shapes that I recognize, basically surfaces that I recognize? One way is to complete the square. And how do I complete the square? So basically I look at the first term, and that's the x to power 2 term, and then xy term, and I divide b by a at 2, and then basically I want to start with a times x plus b over 2ay to power 2. And then I know that this is not going to be the entire thing. I know that there should be some y squared term added to this, but this y squared term is not cy squared anymore. So I have to figure that out. And how, that's the basically expand the parentheses to power 2, the completed square, and you get x squared plus b over axy plus b squared over 4a squared y squared. And this basically what you end up with, because you added that and all of this is multiplied by a, you will have c minus b squared over 4a for y times y squared for the remaining terms, basically. And so this is the completing the square. Now, what comes to mind is that what shape is this telling me? Z equal to this. And again, this is very similar to how we did it for x and y, except that instead of x, you will have this, right? And it turns out if the coefficient over here and this coefficient are basically different signs, then this is going to be a hyperbolic paraboloid. And that's when this coefficient and a are different signs, then it's going to be a hyperbolic paraboloid. That's a saddle point. If the coefficient of y squared is 0, then you get a parabolic cylinder. If the two coefficients have the same sign, then you will get a paraboloid out of this Taylor polynomial, basically. So the approximation, it's either going to look like a hyperbolic paraboloid and or parabolic cylinder, or a paraboloid, basically. And so what I'm not saying in here is that these are all under condition that when we started, not all of A, B, and C were zero. So not all of them were zero, basically. And so that's where we starting with. Now that we're at this point, and we figured this out, does this look any familiar, basically? Over here, if I have C minus B squared over C times 4AC over 4A, which is this term, and I multiply that by A, it would be a negative value, and you can see that the top part is actually the discriminant. That actually tells you that discriminant is going to be negative. Over here, being zero, again, it tells you that 4AC minus B squared has to be zero, which is the discriminant again. And on the bottom, it says that basically the discriminant is going to be positive. It's going to be positive. So that's how it works. Now let's go back to the shapes and take a quick look at them. So now that I have these shapes, and so you can see the discriminant is positive. You can see ABC. Let's change it a little bit. Now, if I look at this, basically, this shape that I have, and I have made it so it looks like ax squared plus bxy plus c y squared, and a and b I can change. Let's see if I change a and b, and I make the A go this way, I get a saddle point. Then I can play this a little bit, and I can get another, basically, paraboloid. And at some point, it's very subtle, but you can see that the cylinder forms, and the cylinder is when you have infinitely many critical points, and they're all either maximum or minimum. And so you see all these different shapes can form by changing these. And so that's how it basically works. And so one thing that I didn't mention is this. When we're talking about discriminants being positive, let's say discriminants being positive, so discriminant, which in this case is going to be for AC minus B squared. If this is positive, which is going to be then the second derivative at A and B with respect to x, and second yy of A and B minus the mixed derivative of A and B to power 2. If this is positive, which we figured out is going to give us one of those paraboloids, then if f sub x of A and B is positive, that means that, let's see, if this is positive, and then if fxx of A and B is positive, then I can comfortably say that in the direction, the curve in the direction, or tangential line in the direction, the curve in direction x, I drew it right there. The curve in the direction x is going to be basically it's going to look like, because it's positive, smiley face. So it would be concaved up. And if I have a concave up, that means that I have a Lokman. Right? So these things actually come in handy. So that's that sort of things that you have. It's just, it means that if I know that the Lokman or Lokmax exists, then I can go back to f sub xx or f sub yy, and they will tell me if I have a concave up or concave down. And for example, if fxx, which is not the case here, if fxx was negative, then I will have the frowny face and a local max. And it's still the same way, because then you can take it to when you know that there is a Lokman or Lokmax, you can take it back to your Calc 1 and figure that out. And so here is how it goes. Basically, I'm making it both go, play it a little bit, and then you will have that's the frowny face, basically. And so that's it. That's the end of the story for now, and maybe some other stuff later.